Hello everyone, and welcome to the first video installment for Mrs. Scott's biology class. Today we're going to focus on properties of water. Now, water is very interesting, and before I go on with the list of the properties, I'm going to have you guys watch a short video on the properties of water.
Imagine an Earth without water, life without water. We find it everywhere, in the atmosphere and below our feet. 3/4 of the Earth's surface is covered by this essential liquid. It's a difficult thing to imagine life without water, because our own survival depends on it. In fact, water is vital to the existence of all forms of life on Earth. Water, or H2O, is an unusual compound with amazing properties. These unique properties are what make it so important to life. First of all, water happens to be the only substance on Earth that can be found naturally in all three states, as a solid, a liquid, and a gas. It is rare in that it actually expands as a solid, which is why ice can float. Pure water is essentially colorless, odorless, and tasteless. Water has a neutral pH, which means it is neither acidic nor basic. Water has been called the universal solvent because it can dissolve many substances. Wherever water goes, either through the atmosphere, the earth, or through our bodies, it takes along valuable chemicals, minerals, and nutrients. This is one reason why water accounts for about 70% of the weight of a cell, which is the building block of life. Water has high specific heat, which means it absorbs a lot of heat before it changes temperature. This is why water makes a great coolant. This is also why oceans, lakes, and water vapor in the atmosphere help to regulate the Earth's temperature. Water molecules are sticky. They attract to each other, which is why water tends to float together, fall as raindrops, and bead up on the surface of a leaf. This property is the result of cohesion. To understand cohesion, let's imagine we're recreating a water molecule. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Because of the molecule's arrangement, and the electronegativity difference between the hydrogen atoms and the oxygen atom, the molecule becomes polar. The oxygen atom has a negative charge, while the hydrogen atoms have a positive charge. Since we all know opposites attract, the oxygen atom will stick to a nearby hydrogen atom. The result is a strong bond. Surface tension is a result of cohesion and is the measure of how difficult it is to break the surface of a liquid. We can observe the high surface tension of water by watching this mosquito step onto its surface, or this insect as it struggles to free itself from a droplet. Surface tension is also what causes a water droplet to take a spherical shape. Water is the most cohesive of all non-metallic liquids. Adhesion is similar to cohesion, but refers to 2 different surfaces or molecules with an attraction to one another. This is why the droplet sticks to this leaf. Along with cohesion, adhesion is responsible for a phenomenon called capillary action. Capillary action is the force that pulls water upward against gravity through a narrow tube. This is an essential property for plants, which rely on capillary action to pull water from their roots up to their leaves. So it's pretty obvious that water is important stuff. Humans rely on it for personal consumption, as well as things like industry, energy production, and agriculture. But we sometimes have a tendency to use more than we need, and pollute what's left. We need to make sure we keep it pure and plentiful.
Okay, so from watching the video and from living everyday life, you know that water is important for all living things. Now, the average person is 60 to 70% water, babies are 78% water, and our brains are actually 90% water. So you might want to take a break and go and get a glass of water while you're watching this video. Now, 70% of all of our cells are water as well. Now, the video discussed this, but I want to list them for you in case you didn't take notes during the video. Why is water important to cells? Why is water important? It can be found in 3 states, so solid, liquid, and gas. It has a neutral pH, so it's neither acidic nor basic. We're going to talk about what those 2 words mean in just a moment. It is a universal solvent, which means it can dissolve a lot of different substances. It can absorb a lot of heat. Now, the video discussed that particular property is important for keeping the planet cool, but it also is important because it keeps our bodies at an optimal temperature, and it allows our bodies to remain in homeostasis, maintaining that internal environment. Now, water molecules are sticky because they are polar. What polar means is that the molecule itself has a positive charge at one end, that would be the hydrogen ends, and then a negative charge on the other end. Okay, that means that those positive ends want to go and stick to other molecules. Now, the stickiness of water molecules is described with 2 different terms. The first is cohesion. So cohesion is the attraction between molecules of the same substance. This is why we have water molecules that are attracted to each other, because of this cohesion. Now, cohesion results in high surface tension, so this is why we have things like beautiful oceans and rivers and streams and waterfalls, but it also helps to form simple things like water droplets. Now, adhesion is slightly different from cohesion because adhesion is the attraction between molecules of different substances. So cohesion allows water droplets to form, allows water to be sticky and stick to other water molecules, but adhesion allows those water droplets formed through cohesion to actually stick almost to the surface of something different. It can be grass, it can be flowers, it can be the windshield of your car. Anything that is different from water, adhesion is going to allow an attraction between molecules there. So as the video mentioned also, adhesion is really important for plants. It causes capillary action where water is drawn up into the roots and stems of plants, and then the leaves can use that water to hydrate. Now, a few terms the video didn't mention, but I find worth mentioning because you guys will see these later on when we talk about the cell membrane, are hydrophilic and hydrophobic. So hydrophilic means that molecules are water-loving. And this is where polar molecules want to mix with other polar molecules. And water is a great solvent because so many things can dissolve in water. And when you try to mix things in water, you can actually form a very even or equal substance in a cup. So in order to demonstrate that, I have my glass of water, and I'm going to mix a little bit of food coloring into that water. Now, when I mix this, because water molecules are obviously in my glass, and food coloring is a dye that's also polar, what you guys will see is that these molecules of the dye will evenly distribute throughout the glass. Now I'm going to speed up the process using a spoon, but you guys can see now I have this beautiful cobalt blue water, and it's very evenly distributed. So those dye molecules have mixed evenly with the water molecules. Those dye molecules are hydrophilic. Now the other term you guys will need to know is hydrophobic. Now hydrophobic means water fearing. So phobia is a fear. Water fearing is hydrophobic. In this case, we have non-polar groups of molecules that try to get close to other non-polar molecules, and they try to get away from polar molecules. So they're afraid of polar molecules, essentially. They want to get away from them. Now, a great example of a hydrophobic solution, or a non-polar solution, would be something like olive oil. So here's my olive oil. Now, if I take olive oil and I mix it with water, and you guys have probably seen this, if you eat any kind of oil-based salad dressing, usually before you pour it on your salad, you have to give it a good shake and mix it up. Otherwise, if you pour it straight out of the bottle without stirring it or shaking it, you're going to pour straight oil onto your salad. Bleh. Okay, so you mix it up, you try to get the vinegar and other ingredients evenly distributed in that salad dressing bottle before you pour it onto your salad or your food. But once you've mixed it, you've shook it, and then you've poured it, that process slowly starts where the non-polar oil is going to drift back up to the top, and it's going to re-separate itself from those polar molecules. It doesn't want to hang out with them. So if I take some of this olive oil and my glass of water and I pour this, we slowly start to see a layer of oil on the top of this glass. It doesn't want to mix with the blue water that's in my glass. So you see an oil line at the top. Now I can stir it, okay, like you would with your salad dressing, and it mixes a little bit. I could probably pour out a pretty even solution here of oil and water, but if you can see this, the little beads of oil are reforming at the top. They're escaping or getting away from that polar substance, my water, and they're forming together. They're afraid of that water, so they float on top. Okay. Now, soap is actually really cool. Soap has a polar end and a non-polar end, and so it makes it a great cleaner because it can dissolve grease or other oils, and it can also dissolve oily dirt. So it has a non-polar end and a polar end. It can mix with water, it can mix with oil, and it's a great cleaner because of those properties. Okay. Now, earlier in the slideshow and on the video that you guys watched, it mentioned acids and bases, and it told us that water was essentially neutral. And if you guys look here on this scale, it says pure water, 7.0. 7.0 is our magic number on our pH scale. That is neutral. Our scale for pH goes all the way from 0 to 14. Now, the pH scale is just a measurement system. It indicates how many hydrogen ions are in a solution, or the concentration of those hydrogen ions. Now, an acid is any compound that forms hydrogen ions in solution. Our acids on that scale are going to be the solutions that have pH values below 7. So anything from 0 to, let's say, 6.5, that's a good number, are going to be considered acids. Acids are usually pretty dangerous. The lower the pH, the more dangerous they become. Acids with very low pHs, like battery acids, can actually burn your skin and cause physical damage if you get them on your skin or your clothing. Other acids you guys might be familiar with that are not as dangerous, that won't burn your skin, and that you can actually eat are things like white vinegar, balsamic vinegar, which is great on salads, and then citrus, so lemons, oranges, grapefruit. They are all acidic, but they're not dangerous that they're going to burn your skin. Now, if you got any of these things, say, in your eye, that would actually hurt you. But eating them is perfectly safe to do. Now, on the other end of the scale, we have bases. So bases are compounds that produce hydroxide ions in solution, and hydroxide symbol is OH negative. Now, basic, or you can call them alkaline solutions, contain a lower concentration of hydrogen ions and usually have a pH above 7, and those go all the way up to about 14 on our pH scale. Now, a pH of 14 or 13.5, those can actually burn you too. So things like ammonia and bleach, if you get those on your skin, if you don't rinse them off and try to neutralize them or get them off of your skin, they can actually burn your skin. They can damage your clothing. Okay. Now the pH in our body, in most of our cells, usually we try to keep that pretty neutral. So 6.5 to 7.5. And there are a lot of mechanisms in our bodies, a lot of processes that help to maintain that neutral pH in our bodies. Now, if the pH changes, this can affect the chemical reactions that are taking place in all of our different body cells. pH changes can affect how our organs work. It can affect how we feel as a whole. And not being able to regulate and adjust that pH level can eventually cause death. So controlling our pH in our bodies, again, important for maintaining homeostasis. So here is just one picture. I have another one that I'll show you guys in just a moment on this show. But this is showing acidity levels and how alkaline something is on our pH scale. So things that you might be familiar with on the acid side over here would be things like battery acid. This includes the acid that's actually in the little AA, AAA, C-sized batteries that you guys might put into video games or flashlights. Those actually contain a small amount of acid, and breaking a battery is actually very unsafe. If you guys ever break a battery, you should be very cautious in cleaning it up because that acid can hurt your skin. Stomach acid, the name itself tells you that it's acid. Its pH is about 1.5. We're going to talk about how that can be changed if necessary in just a moment. Lemon juice, apples are actually acidic. Tomatoes, black coffee, and then normal rain. Some people would say, why rain? Rain is water, but there are a lot of pollutants in our environment and up in the atmosphere that those water molecules actually catch onto and then bring down to the earth with them when they hit the planet. So their pH is essentially a little lower, and they become a little more, that water becomes a little more acidic. Milk is acidic. And then water, there right in the middle, you guys can see water. Now, as we move up to basic solutions, you guys see things like blood. Blood is still within our neutral range, but it is slightly acidic. This helps actually if bacteria or other organisms get into the bloodstream, that acidity level or that basic level, alkaline level, can actually kill off some of those organisms. Seawater, baking soda, borax, milk of magnesia, these are things that you might see in your house. They're pretty common in households. And then as we get up to the higher pHs, we have ammonia cleaner, bleach, and then drain cleaner. These are all very dangerous. Again, if you get them on your skin, they can burn you. Okay, here's another image just showing foods and things that you might eat on a regular basis, showing if something is acidic or basic. And you can find all of this information on the internet if you're interested in finding out the pH, the exact pH of soda or a certain type of fruit. It's very easily found online. Okay, now earlier I mentioned stomach acid, and I said that there are things that you can take that can neutralize that stomach acid. Now, those are called buffers. So weak acids or bases can react with strong acids or bases and can change essentially the pH. Now, buffers are pretty common in medications that are used. A lot of different heart medications are actually buffers. They can lower the pH of blood. But some common ones that you can find at the drugstore and buy over the counter would be Pepcid AC, which is an acid reducer. If you ever get heartburn, it can essentially lower the acidity level or raise the pH up to a neutral level in your stomach. Tums do something very similar where they too can raise that pH and make it closer to 7 so that you're not having that burning heartburn in your chest. And then baking soda is also a great buffer. It can lower the pH if you're cooking with it so that food is not as acidic tasting. It's also a great deodorizer, and baking soda is used a lot in cleaning. Okay, well that concludes our properties of water lecture. Here's our water once again separated from that oil. I hope you guys enjoyed the video and bring any questions that you might have to class tomorrow when we discuss this.